In this video, we're going to learn about electron affinity, which is the energy absorbed or released when an electron is gained by an atom. Now, we know that processes that are exothermic have negative energy values, and processes that are endothermic have positive values. Um, in general, because electrons are attracted to nuclei, electron affinities will be negative because they'll be exothermic and rather favorable processes, but there are definitely exceptions. And if we look at the periodic table, we can see lots of electron affinities. There isn't really a trend that you can see as clearly, either vertically or horizontally, as you can see with, for example, ionization energy or atomic radius. But we can talk through some predictions and some general trends. So let's look within a group. We can see that as you go down a group, the from aluminum down to thallium, we can see that the process becomes less exothermic, meaning less favorable. We still are talking about gaining an electron, a process where an electron at least has some association with a nucleus, which is going to be favorable because of the attraction between the two. But because thallium is so large and has a lower effective nuclear charge, that attraction is not going to be quite as great as you have in the case of, say, aluminum. On the other hand, you might be wondering about boron, why it doesn't have the most negative value in the group. And actually, this is something that we can see across all of the period 2 elements. Boron is not as negative as aluminum. Carbon's electron affinity is not as negative as silicon's, et cetera, et cetera. And the explanation that we can give is, although the added electron is going to be very close to boron's nucleus, given that boron would be adding in the second shell and not the third, fourth, fifth, or sixth shell, what we can say is that because the second shell of boron is so small, there are a lot of electrons in a tight space, and adding an extra electron is going to lead to some repulsion. That repulsion doesn't entirely override the favorability of adding an electron to a boron's shell, but that's going to make it so that there's just a little bit less favorability than putting the electron into a larger shell, as in the case with aluminum. Once we hit aluminum, that's like the sweet spot where you're in the third shell. That extra electron is in not quite as tight a space with a bunch of other electrons, and yet it still is quite attracted to the nucleus, which isn't as far away as you have in the case of gallium, indium, or thallium. So going across a period, we can see even less clear trending. In general, effective nuclear charge is going to correlate with electron affinity, such that as you increase the effective nuclear charge going across, you increase the attraction that the nucleus has on this added electron, making it a more favorable process and therefore a more exothermic process of adding an electron. That's why we have less exothermic in the case of boron and more in the case of fluorine. But there are exceptions. There's nitrogen and there's neon. And actually, those aren't the only endothermic processes. And what we have to do is look at all of the cases of these endothermic electron affinities and see maybe they have something in common. Well, if we look over here at beryllium and magnesium, they're endothermic. And the reason for it is that if you already have a full S shell or subshell, adding another electron means adding it to a P, which is of a higher value, higher energy value. And so that is going to be an endothermic process. And we see that with beryllium and magnesium, not actually further down the group of group 2. But we also have something similar in the case of all of the D10s. If you go to zinc, cadmium, and mercury, they're all the D10s. And whether it's 3D10, 4D10, or 5D10, if you're adding another electron, that electron would go into the corresponding P, and that just would be something of an endothermic process. We can also see that in the case of, say, helium and the rest of the noble gases. Helium is an exception, I suppose. It's S. S2, but adding an electron to an S2 means adding to the next S2, next S as well. In the case of neon, we're at the 2p, which is full. That would be adding an electron to the 3s. Adding an electron to argon would be putting it into the 4s. And so that explains why these would be endothermic processes, because we're adding to a higher energy level. Finally, there are a couple of exceptions where you're basically going from a half full subshell to something more than half full. For example, a D5 like manganese, um, it's D5, so every D orbital has one electron in it. If you add another electron, it's pairing, and that pairing in a tight space, as with a smaller subshell, that is going to be an endothermic process. If you go down actually to 4D below manganese, you'll find it is a slightly exothermic process, but it's only slightly exothermic because there is that repulsion. In the case of manganese, it's such a small space that it renders the whole process to be endothermic. And similarly with nitrogen, if you add another electron to nitrogen, it is pairing in a 2p orbital. And because that 2p is so small, that repulsion is rather significant, and that's why we have an endothermic process. Phosphorus, you don't see it endothermic. It's marginally exothermic, but again, that's because the 3p is a bit bigger, so pairing up in the 3p isn't quite as bad as pairing up in the 2p, which is smaller. Anyway, that's all on electron affinity. Hope this video has been helpful. Feel free to leave any questions or comments in the comments section below, and thanks for watching.